In the second video for Chapter 8, we're going to continue our discussion about special senses and specifically focus on hearing and equilibrium. And both of these structures are dealt with in the ear. And because we're not dealing with chemicals, now we're going to look at mechanoreceptors. And that's because we're going to look at movement. And so there are different organs that house the receptors for each of these senses, whether it's going to be for hearing or it's going to be for equilibrium. Here's an overview of all the structures of our ear. We have this external or outer ear. This is only involved in hearing. Middle ear, this is only involved in hearing as well. However, our internal ear, this is involved in both hearing and equilibrium. And for the next couple of slides, we're going to go step by step of the different functions of each of these structures, starting from this external ear and then ending at our internal ear. Let's start off with our external ear. Once again, this is only for hearing. The first noticeable structure that we see, and the only visible one that we know and can easily point out, is the auricle, and we also call it the pinna. And the function of this is to collect and direct all those sound waves into the auditory canal. From here, all of the sound waves that we collect, we're going to direct that towards our tympanic membrane through this long canal called the auditory canal, or also known as the external acoustic meatus. And so that function is to direct that sound waves to the tympanic membrane. And also, this is that narrow chamber. This is found within the temporal bone. Now we're going to move on to the middle ear, also involved in hearing. Once we collect all that sound and we bring it towards our external acoustic meatus, now all that sound can cause vibrations of this tympanic membrane. And so the function of this is going to vibrate with sound. And so the tympanic membrane, we know it also more commonly as the eardrum. From here, once we vibrate this tympanic membrane, in turn we're going to move these three small bones. We call them the collectively auditory ossicles. And so the small first bone we have here is the hammer. We also call it the malleus. Second one is the anvil, also called the incus. And then this last one over here is the stapes, also called the stirrup. So collectively these will move in response to movement of the tympanic membrane. Okay, so it's going to move in response. Another way we can write this is it's going to transfer those vibrations from the tympanic membrane to the oval window of the inner ear. And the oval window is this structure over here, and we're going to see why that's important in a little bit. And so by doing that, as we move these ossicles, in turn we're going to move this oval window of our inner ear, and that in turn is going to set into motion all the fluid that's found within the inner ear. Okay, also I'm going to put a number 1 over here and then continue writing that over here. So it's going to set the fluids of the inner ear into motion. Now another structure we have here within the middle ear is called the auditory tube. We also call it the pharyngotympanic tube also, or canal. And what this does is it allows for equalization of pressure during yawning, and otherwise it's going to be collapsed. This is why when you go in that airplane, they tell you to yawn, you want to open this up to help equalize that pressure. So it allows for equalization of pressure during yawning. And it will be collapsed otherwise. Now finally, the inner ear. We mentioned this is both for hearing and equilibrium. And so looking at these three different structures, they're going to be specific to either equilibrium or to hearing. The first structure here we have is the vestibule. The vestibule, this is what we have for what's called static equilibrium. In static equilibrium, this is when you do move your head up or down, left and right, and this gives you the sense of positioning of your head. Semicircular canals, these are for dynamic equilibrium. So these are for more fast-paced movements, angular movements. When you go on that roller coaster ride, where's your orientation? And then finally we have the cochlea, and the function of this is for hearing. Now I'm just going to do a quick review, really quick, of hearing, because majority of these structures are for hearing. And so we're going to collect all that sound waves here with our pinna, send that down through our external acoustic meatus, cause then the movement of this tympanic membrane, which in turn moves your three auditory ossicles. Once these move, this in turn is going to shake up your oval window. Oval window also can move all the fluid here found within your inner ear. Specifically, it's going to move all that fluid, and it's going to stimulate cells here within our cochlea for our interpretation of your sound. Okay, so that's how sound's all going to work. And then we also have more fluid found here within these semicircular canals. And then, of course, more fluid here in your vestibule. And we're going to go over then how we can determine the movement of your head looking at static equilibrium. And so here we have receptors found in the membrane sac of the vestibule. And that's what we call the macula. Okay, here's our vestibule, this entire region over here. So we're going to ignore everything on top. And we have this nice membrane surrounding this inner region over here, and that's the macula. And what the macula is going to do is going to help report the position of the head when there's a change in gravity. Now, how does it do that? Well, the macula actually is designed to have certain structures to help assist us in reporting this gravity. Okay, so if we take a cross-section of your membrane, that macula, we notice on the very surface, so the innermost layer here, we have these stone-like structures. It kind of looks like chalk stuck in jello. And these structures, these are actually called stones of calcium salt. So they're otoliths. And otoliths, basically stones of calcium salts. This membrane, majority of this is going to be composed of this jelly-like substance. And that's called the otolithic membrane. Now, embedded in here, we have this layer of cells. Here we have the macula. Here's our entire hairs. So the hair cells and hair tufts. And all these hair tufts are embedded within our otolithic membrane. Now, what happens? Anytime we move our head, so here your head is upright, you're going to move your head downwards. What happens? Well, these otoliths, because they're made of those stones embedded here within your otolithic membrane, when you move your head in a certain direction, because these are pretty heavy, that in turn is going to move all of this entire autolytic membrane. And once again, what's embedded in that autolytic membrane? All of those hair cells, so those hair tufts. And so as you move your otoliths, in turn you're moving your membrane, and in turn you're also going to be moving all of these hair cells. Now once these are stimulated, what happens? We can receive that signal, and we're going to send all that signals down into all of these neurons, and eventually collectively all of these neurons, all the axons of these neurons, collectively form the vestibular nerve. And so what happens? All the movement activates the hair cells, and it's going to send the impulses to the cerebellum through the vestibular nerve number 8. Okay, and remember, cerebellum, this is for your balance, for your coordination, and this helps maintain and direct your entire state of where you're going up and down, left and right. Now, dynamic equilibrium, this occurs if that head moves the cupula, and then the cupula is going to drag against what's called the endolymph in the canals. When the body moves. Okay, and this is going to stimulate hair cells and trigger impulses that are going to be transmitted up the vestibular nerve towards the cerebellum, so then we can also help direct the situation and movement of which direction we're going. Now this movement will, at a constant rate, will eventually stop turning off and stimulating these hair cells to send messages up to your cerebellum. And so over time, what happens? Well, you're not going to have that sense of motion until your speed or direction of your movement changes once again. And so if you look at figure skaters, they can continue on in, let me just move this picture really fast. So we're initially, when a figure skater starts moving, we're going to stimulate all of this fluid called endolymph. That's going to stimulate this cupula, and that's going to tell them which direction they're going. But because they're going to continue to go in their constant direction for a long time, if they don't change the direction, well, they're not going to know that they're actually continuing to spin, so they're not going to get dizzy. Now, let's look at this cross-section and where exactly this cupula is and this ampulla and how dynamic equilibrium works. And so we're going to focus on the cupula of the crista ampullaris, which is this structure over here, and this is found within those semicircular canals. So here's a cupula of this crista ampullaris. In here we have receptors that are found in each of the semicircular canals. And these are going to respond to angular or rotary movements. Meaning you can go up and down, you can go at this angle, or you can also go side to side. Now when that head moves, we mentioned this again, the cupula will drag against the endolymph with the body's motion. Now, whatever plane you're going to move in, that's when you're going to cause the dragging of all that lymph and all that fluid against your crista ampullaris. Okay, so there's kind of a lot of terminology. Let's see what this looks like. So once again, here's all of that endolymph. Here's all these hair cells found within your cupula. And then down here we have all of those axons for all of these hair cells. Okay, so here we're turning in this direction. When you turn in one direction, you're forcing the flow of the endolymph in the opposite direction. As you move that endolymph, in turn you're going to be moving the cupula, the crista ampullaris, and that in turn is going to start stimulating all of these hair cells found in that cupula to get it sent off that message that they're being stimulated. You're going to send that message down towards your axon, and that in turn is going to go send that message down towards your cerebellum that you're moving in a certain direction. So we're going to send the signals to the vestibular nerve. In the cerebellum, and then this movement at a constant rate will eventually stop sending those signals. And we just mentioned already, and you won't have that sense of motion until you change your speed or direction of your movement. Now, another structure we have here is the spiral organ of Corti, and this is going to be dealing with hearing. And so all of this spiral organ of Corti, this is found within the cochlea. So now we're going to focus our attention down here. So once again, static equilibrium deals with your vestibule. Dynamic equilibrium deals with your semicircular canals. Cochlea deals with your hearing. And so this spiral organ of Corti is within that cochlear duct. It contains what's called the tectorial membrane. That's going to bend hair cells, and we have a cochlear nerve. That's attached to hair cells. It's going to transmit nerve impulses to the auditory cortex on that temporal lobe. Let's take a closer look at what this looks like. Here is a cross section of that cochlea. And so let's just go back here really quick. We're going to cut it this way, and we're just going to focus on this cut over here. So here's that cross section. We notice here within this cochlea, we have perilymph up here, so it's that fluid over here. We also have perilymph down here, and in the middle, we have endolymph. Now this region right over here is pretty unique. This is called the spiral organ of Corti, and this is going to be the focus of what we're going to be looking at of how it gives rise to hearing. And so here, we can blow that up a little bit, and we're going to notice we have several structures. We have this one membrane up here. This is called the tectorial membrane. Oh, you hear that popo. Someone's speeding. Down here we have a basilar membrane. Okay. Here we have all our hair receptor or hair cells. Okay. Now how does this all work? I'm just going to go back to the illustration right above. Here's this tectorial membrane that we just pointed out. And here's that basilar membrane down here. And of course all of our hair cells. Now as our tympanic membrane starts shaking up all of those auditory ossicles, in turn those auditory ossicles is going to move that oval window. Oval window in turn is going to start shaking up all of this endolymph found in here. This in turn, all this endolymph is going to start moving along this basilar membrane. Okay, now as this basilar membrane moves, so this is the basilar membrane, we're going to go back to this illustration. As this moves ups and down, we notice right here we have all of these hair cells, these hair receptor cells right on the top. That comes very close into contact with our tectorial membrane. So as this basilar membrane moves back and forth, in turn, all of these hair cells are also going to come into contact with our tectorial membrane. Now, if and when it comes into contact with our tectorial membrane, then these are going to be stimulated. It's going to generate all those action potentials, send that message down its axon, and we're going to send that to the cochlear nerve, and that's going to stimulate and tell our brain that this is now what we're hearing. Okay, so that's exactly what happens and how we can generate hearing. Now, of course, interpretation of hearing and sounds all going to occur within our temporal lobe. However, how can we tell the differences between high-pitched notes and low-pitched notes? Here's our cochlea, and if we flatten it out, so we know it's spiral, kind of like that. But if you flatten it out, it'll kind of look something like this, so flat or also like this. And so we can notice that hair cells, all those hair receptor cells, okay, so all those fibers of those basilar membranes and those receptor cells, they're going to be much shorter and stiffer the closer you are to the vestibule compared to the ones that are farther away from the vestibule. So the ones farther away, they're going to be much longer and they're going to be floppier. Ones closer are going to be shorter and stiffer. And because of this, their length and whether they're stiff or they're floppy, this is going to give rise to the detection of high-pitched notes versus low-pitched notes. And so the ability to send down those vibrations are going to get picked up by each of these fibers. Now here's a great overview of all the different pathways and organs we need to go through for hearing. So external ear, we have our pinna collecting all of that sound. We're going to send that down through our auditory canal and then transmit that towards our eardrum. Eardrum's going to start vibrating, send those vibrations down to stimulate the middle ears, the ossicles of their middle ear, both the hammer, anvil, and stirrup. From here, in turn, we're going to move along our oval window. Oval window is going to shake up our inner ear, specifically all that fluid within the cochlear canals. And then from here, we can start stimulating, moving that basilar membrane. Hair cells, in turn, are going to be moved and stimulate our tectorial membrane. From there, once those hair cells are stimulated by the tectorial membrane, we can send all the signal down towards our cochlear nerve. Okay, and we have all that interpretation of sound within our temporal lobe. Now, to excite those hair cells and that spiral organ of Corti in that inner ear, we have to notice that we don't have a direct transmission from sound from our outer ear towards our inner ear. So we're actually going through a lot of different mediums. We're going through air, we're going through membranes, we're going through bones, and then finally we're going to go through fluids. Okay, so we're going through a lot of things in order for us to interpret all of that sound. And then finally, this last side, great review one more time for hearing. Sound waves coming in, external acoustic canal or external acoustic meatus. Here we have tectorial membrane, or also known as our eardrum, vibrating in response to those sounds. Then we have displacement and movement of these ossicles, auditory ossicles, malleus, incus, and stapes. In turn, we're going to move our oval window, establishing that pressure, move along our basilar membrane, which in turn is going to start vibrations of our hair cells against the tectorial membrane. And then we can stimulate our nerves, our cochlear nerve, and have all that interpretation into our temporal lobe. Okay, so it's a great thing to practice identifying what goes on into each different regions. Now, I know tympanic membrane, it sounds more difficult than eardrum. On your exam, I will take the tympanic membrane or eardrum. And then also for your exam, if you have to identify structures, I will take both of these terms. So whether it's going to be, if you're going to use the term malleus or if you're going to use the term hammer, I'll take both of those. Okay, same thing with incus and stapes versus anvil and stirrup. I'll take either one. All right, and so that concludes the second part of Chapter 8.